A supposed comet is catching the attention of some of the nation's most renowned scientists, as one Harvard professor is raising the theory this may actually be a piece of alien technology.
Right now, something impossible is racing toward our sun at 36 miles every second. This visitor carries ice older than Earth itself, forged in the fires of an alien star system billions of years ago. You'll witness the moment telescopes caught this cosmic intruder, discover why its speed broke every known record, and learn how a teardrop of ancient dust is rewriting our understanding of the space between stars. We're about to explore the third confirmed messenger from beyond our solar system. A wanderer that traveled longer than life has existed on our planet just to reach this moment. Prepare yourselves. We begin. The robotic eye swept across the southern sky, scanning for threats that could end civilization in minutes. What it found instead changed everything we thought we knew about visitors from deep space. The Asteroid Terrestrial Impact Last Alert System telescope in Chile's Atacama Desert had been hunting for dangerous rocks hurtling toward Earth when it detected something that shouldn't exist. A faint dot of light was moving against the stellar background. But this wasn't behaving like any asteroid or comet ever recorded. The object was traveling in completely the wrong direction. Think of our solar system like a giant whirlpool, with the sun at the center and planets orbiting in predictable patterns. Everything born here follows the same general flow, like leaves caught in a stream. But this mysterious visitor was swimming upstream, cutting across our cosmic neighborhood at an angle that defied physics. It wasn't following any orbital path that could keep it bound to our sun's gravity. The Discovery team knew they had found something extraordinary within hours of that first detection. While most space rocks cruise along at speeds measured in thousands of miles per hour, this object was blazing through the void at speeds that seemed impossible. Early calculations suggested it was moving fast enough to escape not just our solar system, but the gravitational pull of nearby star systems too. The implications hit the astronomical community like a thunderbolt. If the math was correct, they were looking at only the third confirmed visitor from interstellar space in human history. The first had been the cigar-shaped mystery called Oumuamua in 2017. The second was Comet Borisov in 2019. Both had sparked fierce debates about their nature and origins. But this new arrival was different in ways that made even veteran astronomers pause. While Oumuamua had been roughly the size of a football field, and Borisov comparable to a city block, early estimates suggested this newcomer dwarfed both previous visitors. We were potentially looking at an object several miles across, carrying ice and rock from a star system so distant that light from there takes decades to reach us. The Chilean telescope had accidentally opened a window into the deep cosmos. Within 72 hours, observatories across 6 continents were swinging their instruments toward the same patch of sky, desperate to capture every photon of light from this cosmic time capsule before it vanished forever into the outer darkness. However, the most shocking revelation was still hidden in the data, waiting to rewrite our understanding of how fast objects can travel between stars. Imagine standing next to a highway where cars travel at the speed of lightning. That's essentially what astronomers discovered when they calculated the true velocity of our interstellar visitor. This object wasn't just fast by space standards, it was moving at 36 miles every single second. To put that in perspective, you could travel from New York to Los Angeles in less than 2 minutes at that speed. A journey that takes a commercial airliner 6 hours would be completed before you could finish reading this sentence. The measurement sent shockwaves through the scientific community because it shattered every previous record for interstellar objects. Oumuamua had impressed everyone by moving at 16 miles per second. Comet Borisov managed 20 miles per second. But this new visitor was traveling almost twice as fast as anything we'd ever seen from beyond our solar system. What makes this speed so remarkable isn't just the number itself. It's what that velocity reveals about the object's incredible journey through the galaxy. Like a detective examining bullet trajectories, astronomers can read the story of cosmic wanderers through their speed and direction. The faster an object moves, the more energy it took to accelerate it, and the more violent the event that originally launched it into interstellar space. This comet had been flung from its home system with such tremendous force that it achieved what scientists call hyperbolic velocity. Think of throwing a ball so hard that it not only escapes Earth's gravity, but keeps accelerating away from our entire solar system. The energy required is mind-boggling, suggesting our visitor survived a cosmic catastrophe of extraordinary proportions. The speed also meant time was running out, unlike asteroids that orbit our sun for millions of years, giving scientists decades to study them. Interstellar visitors flash through our neighborhood like cosmic shooting stars. At 36 miles per second, this object would cross our entire solar system in less than 2 years, spending only months within range of our most powerful telescopes. Observatory directors around the world began emergency scheduling sessions. Every clear night became precious. Every hour of telescope time could capture data that might never be available again. The astronomical equivalent of a gold rush was beginning, with researchers racing to unlock the secrets of this ancient wanderer before it disappeared into the void between stars. But speed wasn't the only thing that made this visitor special. The mathematics of its trajectory held an even more startling revelation. The numbers told a story that seemed too incredible to believe. When astronomers traced the visitor's path backward through time, they discovered something that left even veteran space scientists speechless. This object hadn't just wandered in from the edge of our solar system. It had crossed the vast emptiness between star systems, traveling for millions of years through a cosmic desert where nothing should be able to survive. The proof lay in a single mathematical concept called orbital eccentricity. Think of eccentricity like a cosmic ID card that reveals an object's true nature. Anything born in our solar system has an eccentricity less than 1, meaning its orbit forms a closed loop around the sun. But objects from interstellar space have eccentricities greater than 1, creating open-ended paths that never return. Our mysterious visitor scored an eccentricity of 6.2. That number might sound modest, but it represents something extraordinary in the language of orbital mechanics. For comparison, Oumuamua registered 1.2, while Comet Borisov measured 3.6. This new arrival was following the most hyperbolic trajectory ever recorded, meaning it was more clearly interstellar than any previous visitor. The mathematics revealed an even more startling truth. When scientists ran the orbital calculations in reverse, projecting where this object came from, they discovered it had entered our solar system from the direction of the constellation Sagittarius. This wasn't random wandering. The visitor had followed a precise trajectory across the galaxy, threading the needle between gravitational influences of countless stars. But proving interstellar origin required more than just orbital math. Scientists needed to confirm that our sun's gravity couldn't possibly capture and hold such a fast-moving object. The calculations were definitive. Even if this visitor passed directly through the sun's corona, absorbing maximum gravitational acceleration, it would still possess enough velocity to escape our entire solar system. The confirmation process resembled cosmic forensics. Observatories worldwide contributed precise measurements of position and velocity, building an increasingly detailed picture of the object's path. Each new data point strengthened the case that we were witnessing something unprecedented, the fastest confirmed interstellar object ever detected. Within weeks, the International Astronomical Union made it official. Our visitor received the designation 3I/Atlas, marking it as the third confirmed interstellar object in human history. The I stood for interstellar, while the 3 indicated its place in this exclusive category of cosmic travelers. Yet, the mathematical proof of its alien origin was just the beginning. The object's physical size would prove even more remarkable. Standing next to this interstellar giant would be like an ant facing a skyscraper. Early size estimates suggested our cosmic visitor measured somewhere between 6 and 12 miles across, making it a true colossus compared to previous interstellar objects. To grasp the scale difference, imagine Oumuamua as a football field. This new arrival would be the equivalent of an entire city, complete with suburbs stretching beyond the horizon. The size calculation required detective work worthy of Sherlock Holmes. Since we can't physically measure objects billions of miles away, astronomers had to use light itself as their ruler. By analyzing how much sunlight the visitor reflected and comparing that brightness to its distance from both the Sun and Earth, scientists could estimate the surface area and therefore the approximate size. The Hubble Space Telescope provided crucial measurements when it captured the sharpest image ever taken of an interstellar object. The picture revealed something that looked like a cosmic teardrop, with a bright central nucleus surrounded by a glowing envelope of dust and gas. This coma, as astronomers call it, stretched across thousands of miles, but hidden within that fuzzy glow was a solid core of ice and rock that had traveled across the galaxy. What makes the size so significant isn't just the impressive dimensions. Larger objects can survive interstellar journeys that would completely destroy smaller wanderers. Think of cosmic radiation, like sandblasting, that slowly erodes anything exposed to it. Over millions of years, in the void between stars, this invisible bombardment can wear away entire mountains of ice and rock. Our visitor's substantial bulk meant it had endured this cosmic weathering and emerged largely intact. The outer layers might have been stripped away during its long journey, but enough material remained to create the spectacular display we were witnessing. Every grain of dust streaming away from the nucleus represented matter forged in an alien star system, now mixing with particles from our own sun's domain. The size comparison also revealed something about the violent events that originally launched this object into space. Ejecting something this massive from a planetary system requires extraordinary energy. We're talking about gravitational slingshots involving giant planets, or stellar explosions, powerful enough to hurl city-sized chunks of ice across interstellar distances. But size alone couldn't explain why this visitor was so special. Its rarity factor told an even more compelling story about our cosmic neighborhood. We live in an age when discovering one of these cosmic messengers is like finding a needle in a universe-sized haystack. Consider the staggering improbability of what we were witnessing. In all of human history, with thousands of years of watching the skies, we had confirmed the existence of exactly 3 objects that originated beyond our solar system. That's fewer interstellar visitors than the number of people who have walked on the moon. The rarity makes each detection a scientific event comparable to discovering a new continent. The numbers tell the story of cosmic loneliness. Our galaxy contains over 400 billion stars, many hosting their own planetary systems. Logic suggests these systems should be constantly ejecting comets and asteroids into interstellar space, creating a steady stream of wanderers between the stars. Yet, in practice, finding these nomads requires extraordinary luck and timing. Think of interstellar space like a vast, dark ocean, with occasional visitors passing through our small patch of cosmic shoreline. Most fly by undetected, either because they're too small, too far away, or moving through regions of sky that our telescopes aren't monitoring. The fact that we've spotted 3 suggests thousands more have passed through our neighborhood without being noticed. Each confirmed detection represents a breakthrough in our observational capabilities. Oumuamua was discovered by the Pan-STARRS telescope in Hawaii, which was specifically designed to scan large areas of sky for moving objects. Comet Borisov was found by amateur astronomer Gennady Borisov, using equipment that would have been impossible to afford just decades earlier. Our newest visitor was caught by the Atlas system, a network of telescopes dedicated to protecting Earth from dangerous asteroids. The rarity also creates urgency. Unlike planets or stars that remain visible for centuries, interstellar visitors offer only brief windows for study. By the time we detect them, they're already racing away from us at speeds that make extended observation impossible. Scientists have perhaps months or years to gather data that might not be available again for decades. This scarcity transforms every measurement into precious scientific currency. Each photograph, each spectroscopic analysis, each radar bounce represents irreplaceable information about conditions in alien star systems. We're essentially conducting archaeology on objects that preserve samples of environments billions of miles from home. The 3 confirmed visitors also represent 3 different categories of cosmic wanderer. Oumuamua remained mysterious, possibly asteroid-like. Borisov behaved like a typical comet. Our newest arrival was proving to be something entirely different. Where Oumuamua had been a riddle wrapped in cosmic mystery, this new visitor was writing its autobiography in light. The contrast between our current guest and its famous predecessor couldn't have been more dramatic. Oumuamua had frustrated scientists by revealing almost nothing about its true nature. It showed no signs of the gas and dust emissions that characterize normal comets. Its surface remained stubbornly inactive, offering few clues about composition or origin. Even its shape sparked debates that continue today. This new arrival was the complete opposite, a cosmic exhibitionist putting on a spectacular show for anyone with a telescope. Within days of discovery, observers detected the telltale signs of comet activity. A fuzzy atmosphere, called a coma, had formed around the nucleus, and a faint tail was beginning to develop as ice sublimated under solar heating. The difference was like comparing a locked vault to an open book. While Oumuamua had kept its secrets hidden beneath a mysterious reddish surface, our new visitor was actively sharing samples of its interior composition with every passing day. Each puff of gas and stream of dust particles represented direct evidence of conditions in an alien planetary system. Spectroscopic analysis revealed water vapor, carbon compounds, and organic molecules streaming away from the nucleus. These weren't just random chemicals, but complex substances that told stories about the star system where this object originated. The presence of water suggested formation in a region cold enough for ice to condense. Organic compounds hinted at chemical processes similar to those that occurred in our own solar system's early history. The behavioral differences were equally striking. Oumuamua had accelerated mysteriously as it passed near the sun, leading to speculation about everything from outgassing to alien technology. Our current visitor was accelerating in exactly the way comets should, following predictable patterns that matched computer models of ice sublimation and dust emission. Even the timing was better. Oumuamua had been discovered while already leaving our solar system, giving scientists only weeks to gather data before it faded beyond detection. This new arrival was spotted while still approaching, providing months of observational opportunities as it brightened and became more active. The communication difference was perhaps most significant. Oumuamua had whispered its secrets so quietly that many remained forever unknown. This visitor was practically shouting its story across the electromagnetic spectrum. Every molecule streaming away from our visitor carries a message written in the chemical alphabet of an alien world. Scientists analyzing the comet's emissions were like detectives, examining evidence from a crime scene billions of miles away and millions of years in the past. Each type of gas and dust particle revealed specific conditions that existed when this object first formed around a distant star. The chemical fingerprints were literally extraterrestrial, offering our first detailed look at matter, forged in an environment completely different from our own solar system. The spectroscopic data painted a fascinating picture of alien chemistry. Water vapor dominated the emissions, confirming that this visitor formed in a region cold enough for ice to condense permanently. But the water wasn't alone. Scientists detected carbon monoxide, carbon dioxide, and various organic compounds that suggested a complex chemical environment during formation. Think of these molecules like cosmic DNA, carrying information about their birthplace encoded in their very structure. The ratio of different water isotopes, for example, can reveal the temperature and pressure conditions where ice originally crystallized. Organic compounds provide clues about the types of chemical reactions occurring in that distant planetary system. What made these detections extraordinary was their clarity. Unlike studying exoplanets, where we glimpse chemical signatures in filtered starlight, here we had direct samples streaming past our telescopes. Every gas molecule and dust grain represented uncontaminated material from another star system, preserved in deep freeze conditions during its million-year journey through interstellar space. The chemical analysis also revealed something unexpected about the visitor's journey. Cosmic radiation should have gradually altered the surface composition during the long voyage between stars. Yet, the emissions suggested relatively pristine conditions beneath an outer crust. This indicated the object was large enough to shield its interior from the harsh environment of interstellar space. Some compounds showed evidence of being processed by cosmic rays, creating daughter products that don't exist naturally on planets. These radiation-modified chemicals served as timestamps, providing clues about how long the object had been wandering through the void before arriving in our neighborhood. The ongoing analysis resembled a real-time lesson in comparative planetary science. As more telescopes joined the observation campaign, the chemical catalogue grew more detailed and complex. When astronomers plotted the visitor's path through our solar system, they discovered something that seemed almost choreographed. The mathematics of orbital mechanics rarely produce coincidences, yet this object was following a route that appeared designed for maximum scientific impact. Its trajectory would carry it past multiple planets at distances perfect for telescopic observation, while avoiding close encounters that might gravitationally deflect its path. Consider the precision required for such a passage. Our solar system spans billions of miles, with planets scattered like islands in a vast cosmic ocean. For an interstellar visitor to thread between these gravitational influences, while maintaining an observable path, requires extraordinary geometric alignment. The odds of such perfect positioning occurring by pure chance seemed vanishingly small. The trajectory offered another remarkable feature: optimal viewing geometry throughout its passage. As the object approached the Sun, it would remain visible to telescopes on Earth for months, never disappearing behind solar glare or becoming lost in daylight. This natural scheduling allowed continuous observation during the most active and interesting phase of its visit. Even more intriguing was the timing of closest approach. The visitor would reach its nearest point to the Sun during autumn, when major observatories in both hemispheres could participate in coordinated observation campaigns. Professional and amateur astronomers worldwide would have clear shots at this cosmic target during prime observing season. The path also provided natural experiments in cometary physics. As the object moved closer to solar heating, scientists could watch in real time as ice sublimation increased, dust production accelerated, and the tail grew longer and more prominent. It was like having a laboratory experiment scaled up to planetary dimensions. Some researchers privately wondered if such perfect conditions could be entirely coincidental. The trajectory seemed almost too convenient, too perfectly arranged for scientific study. Yet, the alternative explanations entered the realm of speculation that most astronomers preferred to avoid. The orbital analysis revealed one more crucial detail. This would be a one-time only opportunity. Unlike periodic comets that return every few decades, this visitor was following an escape trajectory that would carry it permanently out of our solar system. 4.5 astronomical units from the Sun, something magical began to happen. At this distance, roughly equivalent to the space between the Sun and Jupiter, solar radiation finally accumulated enough energy to awaken ice that had been frozen solid for millions of years. The process resembled watching a time-lapse movie of spring arriving on an entire world, as ancient materials began their transformation from solid to gas. The physics of this awakening follows predictable patterns that astronomers have studied in countless comets. Sunlight doesn't just provide heat, it delivers energy in precise packets, that can break the molecular bonds holding ice crystals together. When these bonds snap, water molecules escape into space, carrying dust particles along like leaves caught in a cosmic breeze. But this wasn't ordinary ice responding to familiar starlight. These frozen materials had formed around a completely different star, under conditions that existed when our own solar system was still a swirling disk of dust and gas. The awakening represented a meeting between matter from separate stellar neighborhoods, separated by distances so vast that light takes decades to travel between them. The process began slowly, with just a few molecules escaping per second from the warmest regions of the nucleus. As solar heating intensified, the sublimation rate increased exponentially. What started as invisible wisps of gas soon became streams visible to powerful telescopes, then clouds large enough to envelope entire planets. Think of the nucleus like a dirty snowball the size of a small city, composed of ice mixed with rocky debris and organic compounds. As the surface layers vaporized, they exposed fresh material underneath, creating an ongoing cycle of sublimation and dust release. The object was essentially evaporating before our eyes, losing thousands of tons of material every day. The awakening also triggered the formation of the characteristic comet tail. Solar wind, a stream of charged particles flowing outward from the sun, began pushing the gas and dust away from the nucleus. This created two distinct tails, one composed of ionized gas that glowed blue in photographs, and another made of dust particles that reflected yellow sunlight. These tails served as visible proof of the ongoing transformation. Every photograph captured the object in a slightly different state, documenting the steady conversion of ancient ice into space-filling clouds of vapor and debris. When the Hubble Space Telescope turned its unblinking eye toward our cosmic visitor, it captured something unprecedented in the annals of interstellar astronomy. The image that emerged from Hubble's cameras surpassed every previous photograph of an interstellar object in both clarity and detail. Where ground-based telescopes showed only a fuzzy blob of light, Hubble revealed structure and features that transformed our understanding of what we were actually observing. The resolution was so sharp that individual details became visible for the first time. At the center of the frame, a bright point of light marked the location of the solid nucleus, though the actual rocky core remained hidden within its envelope of gas and dust. Surrounding this central beacon, streams of material flowed outward in patterns that resembled frozen fireworks, each tendril telling a story about the forces shaping this ancient wanderer. The most striking feature was the teardrop shape of the overall structure. Unlike the spherical halos that surround many comets, this object displayed a distinctly asymmetrical profile that pointed directly away from the sun. This shape revealed the ongoing battle between solar radiation pressure, pushing material outward, and the weak gravity of the nucleus, trying to hold everything together. Hubble's image also captured something that had never been seen before in an interstellar visitor: clear evidence of active sublimation occurring in real time. Bright jets of material could be seen streaming from specific regions of the nucleus, creating fountain-like patterns that changed position as the object rotated. These jets indicated localized areas where ice was sublimating more rapidly, possibly due to variations in surface composition or exposure to sunlight. The photograph provided crucial data for calculating the object's true size. By measuring the brightness of the central nucleus and comparing it to the surrounding coma, scientists could estimate that the solid core measured somewhere between 1 and 3 miles across. This made it substantially larger than Oumuamua, but smaller than many comets native to our solar system. Perhaps most importantly, the Hubble image served as a historical document. This was the clearest view humanity had ever obtained of matter from another star system, preserved in exquisite detail for future generations to study and appreciate. The revelation was that we weren't just looking at a comet, but at a messenger carrying samples of an alien world directly to our telescopes. Flowing behind our visitor like a cosmic wedding veil, the tale revealed secrets about both its ancient past and its violent present. The teardrop shape wasn't just beautiful, It was a detailed record of ongoing physical processes written across millions of miles of space. Each particle in that glowing stream represented material that had been locked inside the nucleus for billions of years, now liberated by solar heating and scattered across our solar system like breadcrumbs from an alien world. Spectroscopic analysis of the tail revealed a treasure trove of information about the visitor's birthplace. Different regions glowed with distinct colors, indicating the presence of specific molecules and ions. Blue sections marked areas where solar radiation had ionized carbon monoxide and other gases, while yellow and red regions showed sunlight reflecting off dust particles of various sizes and compositions. The tail structure also provided clues about the nucleus's rotation and internal composition. As the object spun on its axis, different regions faced the sun and began sublimating at different rates. This created spiral patterns in the tail, like water spraying from a rotating garden sprinkler, that allowed scientists to calculate the rotation period and identify active regions on the surface. Think of the tail as a fossil record being written in real time. The oldest particles, released weeks ago, had been pushed farthest from the nucleus by solar wind and radiation pressure. The newest material remained close to the source, creating a temporal map of sublimation activity that extended across astronomical distances. The particle size distribution within the tail told another story about the object's internal structure. Large dust grains suggested rocky material mixed throughout the ice, while tiny particles indicated fine-grained dust that had been incorporated during the comet's formation. This mixture revealed details about the environment where the object originally condensed from a disk of material orbiting its parent star. Most remarkably, some particles in the tail contained organic compounds that had survived both the original formation process and the million-year journey through interstellar space. These molecules represented direct samples of chemistry that occurred in an alien planetary system, now available for detailed laboratory analysis. The tail was essentially a time machine, carrying information from another star system directly to our instruments and revealing secrets that no telescope could detect at such vast distances. At a distance of 2 astronomical units from our star, something extraordinary began to intensify. What had been gentle solar heating suddenly became a cosmic blowtorch, transforming our visitor from a quietly sublimating ice ball into an active, dynamic comet, producing thousands of tons of gas and dust every hour. The transition was like watching a campfire suddenly flare into a raging bonfire, driven by forces that operate on planetary scales. The physics behind this transformation involves more than simple heating. Solar radiation carries momentum as well as energy, and when billions of photons strike the comet's surface every second, they transfer that momentum to gas and dust particles. This radiation pressure acts like an invisible hand, pushing material away from the nucleus at speeds of several hundred miles per hour. But the process isn't uniform across the entire surface. Different materials vaporize at different temperatures, creating a complex choreography of sublimation. Water ice begins sublimating noticeably around 3 astronomical units from the sun, while more volatile compounds like carbon monoxide start outgassing much farther away. This creates layers of activity that intensify as solar heating increases. Think of the nucleus like a dirty iceberg floating in space, with the sun acting as a giant heat lamp that grows more intense with every passing day. As outer layers vaporize, they expose fresh material underneath, accelerating the process and creating feedback loops that drive ever-increasing activity levels. The most dramatic changes occur in localized regions where subsurface pockets of volatile materials suddenly breach the surface. These eruptions create jets of gas and dust that can extend for thousands of miles, visible even in small amateur telescopes. Each jet represents a geological event occurring in real time on an object billions of miles away. Solar wind, a stream of charged particles flowing outward from the sun, adds another layer of complexity. As this wind encounters the expanding coma of gas around the nucleus, it creates shock waves and turbulent interactions that shape the developing tail structure. The intensification process also creates spectacular visual displays that make comets among the most photogenic objects in the solar system. What started as an invisible speck of ice was transforming into a celestial beacon, visible across interplanetary distances. As autumn arrived on Earth, our interstellar visitor was approaching the most dangerous moment of its billion-year journey. Perihelion, the point of closest approach to the Sun, represented both the climax of the comet's display and potentially its destruction. At a distance of just 130 million miles from our star, the object would experience heating intense enough to vaporize rock and metal. For a wanderer that had survived the frigid darkness between stars, this solar encounter would test every aspect of its structural integrity. The approach trajectory resembled a cosmic game of chicken, with gravitational forces trying to capture the visitor while its tremendous velocity fought to carry it past the Sun and back into interstellar space. Mathematical calculations showed that escape was inevitable, but the passage would exact a terrible price in lost material. As October progressed, the sublimation rate increased exponentially. What had been a gentle stream of gas and dust became a torrent of material flowing away from the nucleus at thousands of miles per hour. Telescopes worldwide tracked the expanding coma as it grew larger than several planets combined, transforming our visitor into one of the most prominent objects in the night sky. The heating also triggered spectacular outbursts as pockets of subsurface ice suddenly exploded into space. These events, visible as sudden brightening in photographs, represented geological catastrophes on a scale difficult to comprehend. Each outburst released energy equivalent to nuclear explosions, hurling debris across distances measured in thousands of miles. Think of perihelion passage like running through a blast furnace while carrying an ice sculpture. The outer layers inevitably melt and boil away, but if the core is solid enough and the passage quick enough, something substantial might survive the ordeal. For scientists, this phase represented both triumph and tragedy. The intense activity made the comet visible to smaller telescopes and provided unprecedented data about interstellar composition. Yet every day of observation brought the visitor closer to the point where solar glare would make further study impossible. The October passage would determine whether this cosmic messenger survived to continue its journey into the outer darkness, or whether it would join the countless fragments of interstellar debris that mark the paths of previous visitors who couldn't withstand our sun's embrace. Astronomers began the most ambitious detective work in human history, following invisible breadcrumbs across 4 billion years of cosmic time. Tracing our visitor's origin required rewinding the motion of every star in our local galactic neighborhood, accounting for gravitational influences that had nudged both the comet and potential parent systems along their paths. This wasn't simple mathematics, but computational archaeology, reconstructing events that occurred when Earth was still a molten ball of rock orbiting a young sun. The challenge resembled trying to determine where a specific raindrop originated by tracking it backward through a hurricane. Stars move through the galaxy in complex patterns influenced by spiral arms, stellar encounters, and the overall gravitational field of hundreds of billions of other stars. Over millions of years, these tiny influences accumulate into major changes in position and velocity. Supercomputers at observatories worldwide began crunching the numbers, modeling the movement of thousands of nearby star systems, and calculating where they would have been when our visitor first began its interstellar journey. Each simulation required tracking gravitational interactions across distances, measured in light years, and time periods longer than complex life has existed on Earth. The preliminary results were staggering. Backward projections suggested the object had been traveling through space for at least 4 million years, possibly much longer. During that time, it had covered distances so vast that light itself would take decades to make the same journey. This wasn't just a visitor from another star system. It was a time traveler carrying samples from an era when human ancestors were just beginning to walk upright. Even more remarkable was the realization that our visitor had threaded between countless gravitational obstacles during its journey. Close encounters with other stars could have deflected its path or torn it apart entirely. The fact that it arrived intact suggested either extraordinary luck or a trajectory that had been somehow protected from major perturbations. The search for the origin point focused on regions where stellar density was high enough to produce frequent gravitational interactions. These cosmic billiard tables, where stars regularly pass close enough to exchange planets and comets, represented the most likely birthplaces for interstellar wanderers. Some candidate parent systems showed intriguing characteristics. Ancient red dwarf stars with stable planetary systems could have hosted our visitor for billions of years before a chance encounter with a passing star provided the gravitational kick needed to achieve escape velocity. The backward tracking also revealed something sobering about the rarity of such detections. For every interstellar visitor we discover, millions more likely pass through our solar system undetected, following trajectories that don't bring them close enough to Earth for telescopic observation. But understanding the journey was only half the story. The incredible duration of that voyage held secrets about survival in the cosmic wilderness. Between the stars lies a desert so vast and hostile that crossing it represents one of the greatest endurance tests in the universe. Our visitor had spent eons traveling through regions where temperatures hover just above absolute zero, where deadly cosmic radiation bombards every surface, and where the nearest source of heat and light remains trillions of miles away. This wasn't a quick hop between neighboring worlds, but an odyssey spanning geological ages, requiring survival mechanisms that most materials simply don't possess. Consider the timeline of this incredible journey. When our comet first began wandering between stars, Earth's continents were still forming, and the most complex life consisted of single-celled organisms. Entire mountain ranges had risen and eroded away during the time it took this frozen messenger to cross the gulf between star systems. The survival challenges were unlike anything terrestrial life has ever faced. Cosmic rays, high-energy particles accelerated to near light speed by stellar explosions, constantly bombarded the traveler's surface. Over millions of years, this radiation could have chemically altered the outer layers, breaking down complex molecules and creating new compounds that exist nowhere else in nature. Interstellar space also contains tiny grains of dust and occasional gas atoms that, at the speeds our visitor was traveling, would strike like microscopic bullets. Think of driving through a sandstorm at highway speeds, except the journey lasted millions of years, and the sandstorm extended across distances greater than the space between planets. Temperature presented another formidable obstacle. Far from any warming star, the object's surface temperature would have dropped to within a few degrees of absolute zero. At such temperatures, most materials become brittle as glass, and even minor impacts could shatter entire sections of the nucleus. Yet our visitor had endured all of these challenges and emerged largely intact. The fact that it was still producing gas and dust upon reaching our solar system proved that substantial amounts of volatile materials had survived the interstellar crossing. This suggested either exceptional luck or internal structures that provided protection from the hostile environment. The journey also involved navigating gravitational influences from every star system along the route. Close encounters with other stellar neighborhoods could have altered the trajectory, accelerated or decelerated the object, or even captured it entirely. The mathematics of such interactions become impossibly complex over cosmic timescales. Most remarkably, the traveler had maintained enough structural integrity to produce the spectacular display we were witnessing. Every molecule of gas streaming away from the nucleus represented material that had survived one of the longest and most dangerous journeys possible in our galaxy. This endurance story was written in the very composition of the tale itself. The 36 miles per second wasn't just a measurement, it was a biography written in the language of physics. Velocity serves as cosmic DNA for interstellar objects, encoding information about the catastrophic events that originally launched them into space and the gravitational history of their subsequent journey. Like forensic scientists analyzing evidence at a crime scene, astronomers could read the story of our visitor's violent birth in the precision of its speed and trajectory. Objects don't achieve interstellar velocities through gentle processes. The energy required to accelerate something the size of a small mountain to 36 miles per second demands gravitational encounters of extraordinary violence. We're talking about close passes with massive planets, stellar explosions that can sterilize entire solar systems, or gravitational slingshot maneuvers involving binary star systems. The speed signature also revealed clues about the stellar environment where this ejection occurred. Different types of star systems produce different velocity distributions for their ejected comets and asteroids. Young, active systems with massive planets tend to fling objects faster than older, more settled arrangements. Our visitor's extreme velocity suggested origin in a dynamic, possibly chaotic stellar neighborhood. Think of interstellar space like a cosmic highway system, with different speed limits depending on the local gravitational environment. Objects traveling at modest velocities might have originated from nearby stars, while high-speed wanderers like our visitor could have crossed much larger distances from more exotic locations. The velocity also provided timing information about the original ejection event. Faster objects cross interstellar distances more quickly, meaning their parent systems existed more recently in cosmic terms. Our visitor's speed suggested it had been launched from its home system within the last few million years, making it relatively fresh in astronomical terms. But speed alone wasn't the whole story. The direction of travel added another layer of information about possible origins. By tracing the trajectory backward and accounting for the motion of nearby stars, scientists could identify potential parent systems that might have been in the right position to launch our visitor millions of years ago. The precision required for such calculations was staggering. Measuring velocity to the accuracy needed for origin tracing meant determining position changes of less than an inch per second across distances of billions of miles. This demanded coordination between observatories worldwide and measurement techniques pushed to their absolute limits. Even small uncertainties in velocity measurement could translate to enormous errors in determining the origin point. A difference of just 1 mile per second in the initial velocity could place the source in completely different stellar neighborhoods. Yet the speed held one more secret about the nature of interstellar space itself. Deep in our galaxy's thick disk, where ancient stars drift in lazy orbits far from the spiral arms, something had violently ejected our cosmic messenger into the void. The thick disk represents one of the Milky Way's most mysterious regions, populated by stars so old they formed when our galaxy was still young and metal-poor. These ancient suns follow orbits that carry them high above and below the main galactic plane, creating a sparse halo of stellar relics that have witnessed billions of years of galactic evolution. Chemical analysis of our visitor's emissions provided the crucial clue to its exotic origin. The ratios of different elements detected in the sublimating ice didn't match the composition of objects formed in regions like our own solar neighborhood. Instead, they suggested formation around a star with much lower concentrations of heavy elements, exactly what astronomers expect from thick disk populations. Think of stellar neighborhoods like different ethnic communities, each with characteristic chemical signatures that reflect their formation history. Stars born in the galactic disk, like our Sun, are relatively rich in heavy elements produced by previous generations of stellar explosions. But thick disk stars formed when the galaxy was younger and had experienced fewer such enrichment events. This chemical archaeology revealed that our visitor carried samples from one of the most ancient stellar environments in our cosmic neighborhood. The ice now sublimating under our Sun's heat had originally condensed around a star that might have been shining when the Milky Way was less than half its current age. The thick disk origin also explained the object's unusual orbital characteristics. Stars in this population move through the galaxy in highly elliptical orbits that regularly carry them through different galactic environments. Such motion increases the likelihood of gravitational encounters that could eject planetary material into interstellar space. But thick disk stars are typically much more stable than younger stellar populations. They've had billions of years to settle into predictable patterns, making violent ejection events relatively rare. For our visitor to have achieved escape velocity from such a system required either an extraordinary gravitational encounter or a more exotic mechanism. Some theories suggested binary star interactions, where two stars orbiting each other create complex gravitational fields that can dramatically accelerate nearby objects. Others proposed encounters with rogue planets or brown dwarf stars that occasionally pass through established stellar systems like cosmic wrecking balls. The thick disk connection also raised intriguing questions about the age of our visitor itself. If it had formed around an ancient star, it might represent some of the oldest preserved matter in our galactic region, carrying chemical fingerprints from an era when the universe itself was fundamentally different. This ancient heritage was written not just in chemistry, but in the very structure of the object itself. Across millions of years of interstellar travel, invisible cosmic bullets had been slowly reshaping our visitor's surface, one atom at a time. Cosmic radiation represents one of the most persistent and destructive forces in interstellar space, consisting of high-energy particles accelerated to near light speed by stellar explosions, black holes, and other violent cosmic events. These particles carry enough energy to break apart virtually any material they encounter, gradually altering the chemical composition and physical structure of anything exposed to them. For our interstellar traveler, this radiation bombardment had been constant throughout its million-year journey. Every square inch of surface had been struck by billions of cosmic ray particles, each impact capable of shattering molecular bonds and creating new chemical compounds that don't occur naturally on planets. The cumulative effect was like being sandblasted by an invisible beam that never stops firing. The process creates what scientists call a space-weathered surface, characterized by microscopic glass beads, metallic nanoparticles, and radiation-damaged crystals. These features serve as timestamps, recording the duration and intensity of cosmic ray exposure. By analyzing the degree of space weathering, researchers could estimate how long our visitor had been wandering between stars. Think of cosmic ray damage like geological erosion, except operating on molecular scales and powered by some of the most energetic processes in the universe. Just as water gradually carves canyons through solid rock, cosmic radiation slowly transforms the outer layers of interstellar objects, creating new minerals and chemical compounds that exist nowhere else. The radiation sculpting also explained some puzzling aspects of the object's behavior. Space-weathered surfaces often develop properties that affect how they interact with sunlight and solar wind. These altered characteristics could influence sublimation patterns, dust production rates, and even the overall brightness of the developing coma. Spectroscopic analysis revealed telltale signatures of radiation processing in the form of unusual molecular species and isotopic ratios. Some compounds detected in the tail could only have formed through cosmic ray bombardment, providing direct evidence of the harsh conditions our visitor had endured during its interstellar voyage. The radiation damage wasn't uniform across the entire surface. Areas that had been shielded by overlying material showed less alteration than regions exposed directly to space. This created a complex patchwork of different surface properties that influenced where and how sublimation occurred as solar heating began. Most remarkably, the radiation sculpting had created a protective crust that actually helped preserve the object's interior. The altered surface materials formed a barrier that slowed heat penetration and reduced erosion from micrometeorite impacts. But this protective shell couldn't hide the object's secrets forever. Solar heating was beginning to penetrate deeper layers, revealing materials that had been shielded from cosmic rays for millions of years. In the vast darkness between stars, countless cosmic messengers travel invisible highways that we're only beginning to detect. The discovery of our third interstellar visitor revealed a sobering truth about the limitations of human observation. For every wandering object we manage to spot, thousands more likely pass through our solar system completely unnoticed, following trajectories that keep them hidden in the cosmic shadows or moving too quickly for our detection systems to track. Consider the observational challenges that make these discoveries so difficult. Most interstellar objects are small, dark, and cold, reflecting virtually no light until they approach close enough to a star for solar heating to begin sublimation. By the time they become visible, they're often already racing away from us at speeds that provide only brief windows for study. The geometry of detection adds another layer of difficulty. Our telescopes can only monitor limited portions of the sky at any given time, creating blind spots where objects might pass completely unobserved. Like trying to spot highway traffic by looking through a keyhole, we see only tiny fractions of the cosmic traffic flowing around us. Think of interstellar space as a vast ocean with occasional ships passing in the night. Most vessels travel routes that never bring them close enough to shore for observers to notice. Only the rare few that pass directly through our local waters or carry bright lights that can be seen from great distances have any chance of detection. The speed factor makes the challenge even more daunting. Objects traveling at 36 miles per second cross our entire solar system in less than 2 years. If they're discovered late in their passage, scientists might have only weeks or months to gather data before the visitors fade beyond the reach of even the most powerful telescopes. Recent advances in sky survey technology are beginning to change this situation. Automated telescopes, like the one that discovered our current visitor, can monitor enormous areas of sky simultaneously, dramatically increasing the chances of catching these cosmic speedsters before they escape detection. But even the most sophisticated survey systems have limitations. Objects approaching from the direction of the sun remain invisible until they've already passed their closest point. Visitors arriving from regions of sky crowded with stars can hide in the stellar background like camouflage ships in a harbor. The realization that we've detected only 3 interstellar objects in human history suggests that dozens or perhaps hundreds of others have passed through our neighborhood without being noticed. Each missed opportunity represents lost scientific data that might have provided unique insights into conditions around distant stars. This hidden traffic raises profound questions about what else might be traveling the cosmic highways just beyond the range of our current detection capabilities. Like cosmic ambassadors from distant worlds, each of our 3 confirmed interstellar visitors brought dramatically different messages about the universe beyond our solar system. The comparison between these wanderers reads like a tale of 3 completely different alien environments. Oumuamua arrived as a mystery wrapped in reddish silence, refusing to behave like any known type of cosmic object. Its elongated shape, mysterious acceleration, and complete lack of visible outgassing made it the ultimate cosmic riddle that scientists are still trying to solve. Comet Borisov played the role of the perfect interstellar ambassador, behaving exactly as theories predicted an alien comet should. It displayed all the classic characteristics of objects from our own solar system: a clear nucleus surrounded by a fuzzy coma, a well-developed tail pointing away from the sun, and spectroscopic signatures that matched familiar chemical compositions. Our current visitor represents something entirely new, a cosmic giant that dwarfs both previous discoveries while displaying activity levels that surpass anything seen before. Where Oumuamua measured roughly the length of a football field and Borisov was comparable to a city block, this newcomer stretches across distances measured in miles rather than hundreds of feet. The size differences alone tell fascinating stories about their respective origins. Small objects like Oumuamua require less energy to achieve interstellar velocities, suggesting they might be fragments knocked loose by relatively gentle gravitational encounters. Medium-sized visitors like Borisov could represent typical comets ejected during planetary system formation. Giants like our current guest demand violent ejection mechanisms that hint at catastrophic events in their parent systems. Think of these three discoveries like archaeological artifacts from different civilizations. Each provides unique insights into the conditions that existed in alien stellar neighborhoods, the processes that launched them into interstellar space, and the survival challenges they faced during their long journeys to our cosmic doorstep. The behavioral differences were equally striking. Oumuamua remained largely inert throughout its passage, offering few clues about its composition or internal structure. Borisov became modestly active as solar heating increased, producing enough gas and dust to confirm its cometary nature. Our newest arrival transformed into a spectacular light show, generating massive clouds of sublimating material that made it visible to telescopes worldwide. Velocity comparisons revealed another layer of information about their cosmic biographies. Oumuamua's relatively modest speed suggested origins in the local stellar neighborhood. Borisov's intermediate velocity pointed to sources somewhat farther away. The extreme speed of our current visitor implied ejection from regions of the galaxy where gravitational encounters are more violent and dynamic. Each discovery also represented advances in our detection capabilities and observational techniques. Every molecule streaming away from our visitor's nucleus carried the chemical signature of an alien world forged around a completely different star. The spectroscopic analysis resembled reading an autobiography written in the language of atoms and molecules, where each detected compound revealed specific details about the environment where this object originally formed. Unlike studying distant exoplanets, where we glimpse chemical signatures filtered through atmospheres and stellar radiation, here we had direct access to uncontaminated samples from another planetary system. Water dominated the emissions, but this wasn't ordinary terrestrial water. Isotopic analysis revealed subtle differences in the ratios of heavy to light hydrogen atoms, providing clues about the temperature and pressure conditions that existed when this ice first condensed around a distant star. These isotopic fingerprints were like cosmic DNA, uniquely identifying the stellar nursery where our visitor was born. Carbon compounds added another chapter to the alien biography. The detection of carbon monoxide, carbon dioxide, and various organic molecules suggested formation in a region where carbon chemistry could occur freely, possibly within a debris disk surrounding a young star. These materials had been locked in deep freeze for millions of years, preserving chemical conditions that existed when alien worlds were still forming. Think of the nucleus like a geological core sample from another star system, with different layers recording various epochs of formation and evolution. As solar heating penetrated deeper into the structure, it exposed materials that had been shielded from cosmic radiation and preserved in pristine condition throughout the interstellar journey. The organic compounds were particularly intriguing because they suggested chemical processes similar to those that occurred in our own solar system's early history. Complex carbon-based molecules require specific conditions to form and survive, including adequate time, appropriate temperatures, and protection from destructive radiation. Some detected species could only have formed through processes that operate over geological timescales, indicating that our visitor's parent system had achieved stability for extended periods. This wasn't debris from a young, chaotic stellar environment, but material from a mature system that had time to develop complex chemistry. The metal content told yet another story about stellar metallicity and planetary formation processes. Heavy elements detected in the sublimating gases suggested that the parent star had been enriched by previous generations of stellar explosions, similar to conditions that existed when our own solar system formed. Most remarkably, some compounds showed evidence of having been processed by cosmic radiation during the interstellar journey, creating daughter products that served as timestamps for the duration of the voyage. This chemical archaeology was providing our first detailed look at matter forged in an entirely different corner of the galaxy. Across 6 continents, astronomers were racing against time itself to capture every possible photon of light from our rapidly fading cosmic visitor. The urgency resembled an archaeological dig where the artifacts were dissolving, even as scientists tried to study them. Every passing day carried the object closer to solar conjunction, the point where it would disappear behind the sun's glare and become unobservable for months. When it finally emerged on the other side, it would be racing away from us at tremendous speed, growing fainter with each passing hour. Observatory directors worldwide scrambled to reorganize their observing schedules, canceling routine projects to focus telescopes on this once-in-a-lifetime target. The Hubble Space Telescope, normally booked solid years in advance, received emergency observing time to capture the highest resolution images possible. Ground-based facilities from Chile to Hawaii coordinated their efforts to maintain continuous coverage, as Earth's rotation carried different sites into darkness. Amateur astronomers joined the campaign with remarkable success, proving that citizen scientists, equipped with modern CCD cameras, could contribute meaningful data to professional research programs. Their photographs and measurements filled gaps in the observational coverage and provided valuable confirmation of results obtained by larger facilities. The data collection effort resembled a massive scientific relay race, with each observatory contributing pieces of a larger puzzle. Optical telescopes measured brightness changes and tracked the object's motion against background stars. Infrared instruments analyzed heat emission from the nucleus and mapped temperature variations across its surface. Radio telescopes searched for molecular emission lines that could reveal the composition of sublimating gases. Think of each observation like a snapshot of a rapidly changing system, where conditions could alter dramatically between one measurement and the next. Outburst events that suddenly increased brightness by factors of 10 provided spectacular viewing opportunities, but lasted only days or weeks before fading back to normal levels. The race against time was complicated by Earth's orbital motion and changing viewing geometry. As weeks passed, the angle between Earth, the comet, and the Sun shifted continuously, altering the lighting conditions and affecting what features could be observed. Some measurements were only possible during narrow windows of optimal geometry. Weather became a critical factor at ground-based observatories. Clear skies that might normally be routine suddenly became precious commodities when every lost night meant irreplaceable data slipping away. Backup facilities in different climate zones provided insurance against local weather problems. The most frustrating aspect was knowing that this might be humanity's only chance to study this particular messenger from interstellar space. While our current visitor raced towards solar conjunction, mission planners were already designing spacecraft to intercept the next interstellar wanderer before it could escape detection. The European Space Agency had been developing exactly such a capability through their Comet Interceptor mission, a spacecraft designed to wait patiently at a gravitational balance point between Earth and the Sun until a suitable target appeared. Unlike traditional missions that launch toward predetermined destinations, this interceptor would remain dormant until activated by the discovery of a new interstellar visitor. The concept represented a fundamental shift in space exploration philosophy. Instead of chasing targets that were already escaping the solar system, future missions would position themselves to intercept visitors while they were still approaching and could be studied for extended periods. Think of it like having a Coast Guard station positioned along a shipping lane, ready to investigate any unusual vessels that might pass by. The waiting game required extraordinary patience and technological sophistication. Spacecraft systems would need to remain functional for years without active operation, then spring to life within days or weeks when a target was identified. The interceptor would also need enough fuel and maneuvering capability to reach objects with unpredictable trajectories and high velocities. Mission designers faced unique challenges in planning encounters with objects whose characteristics remained completely unknown until just months before arrival. Traditional spacecraft are designed for specific targets with well-understood properties. Interstellar interceptors needed to be versatile enough to study anything from tiny rocky asteroids to giant active comets. The scientific payloads represented wishful thinking made manifest. Instruments capable of analyzing surface composition, internal structure, magnetic fields, and gas emissions would be packed into platforms small enough to achieve the high velocities needed for interstellar intercepts. Every gram of mass would compete with fuel requirements for the complex orbital maneuvers. The timing requirements were equally daunting. From discovery to intercept, mission controllers might have only months to calculate trajectories, upload new navigation commands, and execute the orbital changes needed to reach their target. Traditional mission planning cycles that take years would need to be compressed into frantically paced weeks. Some concepts involved multiple spacecraft working together, with one vehicle conducting a high-speed flyby, while others attempted more challenging rendezvous maneuvers. This approach would maximize scientific return while providing backup capabilities if individual vehicles failed to reach their targets. The ultimate goal was to graduate from passive observation to active exploration, transforming interstellar visitors from fleeting curiosities into thoroughly studied representatives of alien stellar neighborhoods. The sudden appearance of interstellar visitors in our discovery catalogs wasn't coincidence, but the result of a technological revolution that has transformed our ability to scan the cosmic neighborhood. Just 2 decades ago, finding objects like our current visitor would have been virtually impossible. The telescopes and detection systems that existed then were designed for studying distant galaxies and nearby planets, not for spotting small, fast-moving objects racing through the outer solar system. The discovery of Oumuamua in 2017 marked the beginning of a new era in observational astronomy. The transformation began with automated sky surveys, capable of monitoring enormous areas of space simultaneously. Projects like the Catalina Sky Survey, Linear, and Atlas represent a fundamental shift from traditional astronomy, where researchers pointed telescopes at specific targets, to automated systems that photograph the entire visible sky every few nights, looking for anything that moves or changes. Think of these surveys like cosmic security cameras, continuously recording everything that happens within their field of view and comparing new images with archived photographs to identify objects that weren't there before. Computer algorithms analyze millions of measurements every night, flagging unusual detections for human review. The processing power required for such operations would have been impossible just 20 years ago. Modern computers can compare the brightness and position of millions of stars in minutes, identifying the handful of moving objects hidden among the stationary background. These same calculations would have taken months using earlier technology. Improved camera sensitivity also played a crucial role. Modern CCD detectors can capture objects thousands of times fainter than photographic plates used in previous decades. This increased sensitivity allows surveys to detect smaller objects at greater distances, dramatically expanding the volume of space under constant surveillance. The global coordination of survey efforts created another layer of detection capability. When one telescope spots a potentially interesting object, observatories worldwide can quickly provide follow-up observations to confirm its nature and track its motion. This network effect multiplies the effective power of individual facilities. Perhaps most importantly, the scientific community developed new strategies for recognizing interstellar visitors among the thousands of asteroids and comets discovered each year. The orbital analysis software and statistical techniques needed to identify hyperbolic trajectories simply didn't exist until researchers began actively searching for such objects. The detection revolution has revealed that interstellar visitors are probably much more common than anyone suspected. We're not seeing more of them because they're arriving more frequently, but because we finally have the tools to find them. Hidden throughout our galaxy, invisible traffic lanes carry ejected debris between star systems in patterns we're only beginning to understand. The discovery of multiple interstellar visitors has revealed something remarkable about the space between stars. It's not empty desert, but a complex transportation network where cosmic hitchhikers follow predictable routes shaped by galactic gravity and stellar motion. These invisible highways connect every star system in our galactic neighborhood, creating opportunities for material exchange on scales we never imagined possible. Computer simulations of galactic dynamics show how objects ejected from planetary systems don't wander randomly through space, but follow curved paths influenced by the gravitational field of the entire Milky Way. Like rivers flowing downhill toward the ocean, interstellar debris tends to concentrate in specific regions where stellar density and gravitational influences create natural collection points. Think of our galaxy like a vast city with cosmic boulevards, side streets, and traffic patterns that have remained stable for millions of years. Objects entering these routes at specific velocities and directions will follow predictable paths that carry them past numerous star systems during their journeys. Our solar system sits at the intersection of several such pathways. The mapping effort requires tracking not just current stellar positions, but projecting where every nearby star will be millions of years into the future. Stars aren't fixed points, but move through the galaxy in complex orbits that bring them closer together or farther apart over cosmic timescales. These changing configurations alter the invisible highway network continuously. Some routes appear to be more heavily traveled than others. Regions where binary star systems create complex gravitational fields tend to produce more ejected material than isolated single stars. Stellar nurseries, where young systems are still forming, also generate significant debris flows as planetary formation processes scatter leftover material into interstellar space. The highway concept explains why certain types of interstellar visitors seem more common than others. Small, rocky objects require less energy to achieve escape velocity and are therefore more likely to be launched into the network. Giant comets, like our current visitor, represent rarer events that demand extraordinary ejection mechanisms. Observatory planning is beginning to incorporate these traffic patterns into search strategies. By understanding where the invisible highways intersect our solar system, astronomers can predict the most likely directions for detecting future visitors and position survey telescopes accordingly. The ultimate goal is creating a comprehensive map of interstellar transportation routes that could guide future missions designed to intercept or even ride these cosmic currents to other star systems. This mapping effort is revealing the galaxy as a far more interconnected place than anyone previously imagined. We stand at the threshold of a new scientific discipline where ancient artifacts from alien worlds arrive at our doorstep, carrying messages from across the galaxy. Each interstellar visitor represents something unprecedented in human experience, a physical sample from another star system that we can actually touch, analyze, and study in laboratory detail. Unlike astronomy's traditional reliance on analyzing light from distant objects, interstellar archaeology provides direct access to matter forged under alien suns and preserved in the cosmic deep freeze for millions of years. The implications extend far beyond simple curiosity about our cosmic neighbors. These wandering time capsules carry chemical fingerprints that reveal conditions during planetary formation around other stars, providing ground truth for theories about how solar systems develop and evolve. Each detected compound offers clues about stellar metallicity, temperature profiles, and the complex chemistry that occurs in environments billions of miles from Earth. Think of our solar system like a cosmic port of entry, where customs agents, equipped with spectrometers and cameras, examine cargo from distant stellar neighborhoods. Every measurement adds another piece to an enormous puzzle depicting the diversity of planetary environments throughout our galactic region. The archaeological metaphor becomes even more appropriate when considering the timescales involved. Objects reaching us today began their journeys when our own planet looked completely different. They carry samples from an era when different stars dominated the local galactic environment and when the chemical composition of interstellar space bore little resemblance to current conditions. Future developments in spacecraft technology will transform interstellar archaeology from a passive discipline into an active field science. Interceptor missions will allow detailed surface analysis, sample return capabilities, and perhaps even the deployment of landers on particularly large visitors. These direct investigations will provide data impossible to obtain through remote observation alone. The field is also driving advances in rapid response astronomy and international cooperation. The brief observational windows available for studying interstellar visitors demand coordination between observatories, space agencies, and research institutions on scales never before attempted. These collaborative frameworks are establishing protocols for studying even more exotic discoveries that may await us. Perhaps most importantly, interstellar archaeology is revealing the galaxy as a place where material routinely travels between star systems, creating connections and opportunities for chemical exchange across vast distances. We live not in an isolated solar system, but as part of a galactic community linked by invisible highways, carrying messages from worlds we may never visit. The dawn of this new discipline promises discoveries that will reshape our understanding of planetary formation, stellar evolution, and our place in the cosmic neighborhood.